So the first part he talks about, if we have already learned that current can pass through conductors, okay, and there are other type of materials which are semiconductors and insulators. There are three types. We already studied some dielectric, constant, capacitance and all the things earlier, right? So in primarily the conductors, we have a metal or a solid conductors, and the other one is the electrolytes. So here we are talking about the current electricity through metal conductors. So it's basically, if you have a metallic conductor or a metal conductor with length L and you have a cross section area, that means your cross section area is A, so it will have some resistance R and have a resistivity rho for that material. So we know that if there is a potential difference between the two ends, then the charge can flow, some charge Q can flow through this, okay. So the way they measured is current passing through, okay, a particular cross section, okay, current across the area. So the current is defined as how much is the net charge flowing through a specific cross section area in a given time, okay. Is also nothing but, from the differentiation perspective, how much is the delta Q per time, okay. How this matters is, for example, Q depends on, is a function of t, something like say t square minus 3t plus 2 or something like that. This is a charge as a function of time. That means when t equal to 0, only 2 charges go, like that, you know. So then dq by dt, that means you differentiate this, then whatever you get is called a current. So at a particular time, how much is the current, and that's how it is called. Electric current is net charge flowing through a cross section of the conductor, okay. So that's the first topic, which is 3.1 and 3.2. And then he talks about electric currents in conductors. He talks about in general what actually, he gives an idea about, okay. There are 1 gram of water, if you take for example, in 1 gram of water 10 to the power of 22 molecules are there. 1 gram of water contains 10 to the power of 22 molecules. These are like very huge number of molecules, okay. So these molecules are very closely packed so that the electrons are no longer attached to an individual nuclei. That means the electrons are there, but they are freely available in that area. So in some materials, electrons will still be bound. That means they will not accelerate even if we apply the electric field. That's what we call insulators and things like that, okay. So in any case, look at the picture 3.1, figure 3.1. If the electric field, because we always give the electric field direction going from a positive to the negative, okay. So we have a conductor and there is a positive here and there is a negative charge or negative polarity. So you've got a plus q this side and there is a minus q this side. Electric field will be in this direction. So that's the electric field. So if the electric field is in this direction, we already talked about, if current flows in one direction, there is a notation, the electrons flow in the other direction. Electrons direction, and this is the current direction. They are opposite to each other. So that's the reason when we draw the circuits and we say like the current is going this way, the electrons will be going this way. it will be the opposite direction in the for the convention. Okay. So section 3.4 talks about Ohm's law and how Ohm's law is actually, when you have a solid conductor, we know that Ohm's law is nothing but V by V is equal to IR. The resistance is given in such a way R is equal to rho L by area of cross section. We can put this as A or small a. So this is called a resistivity, and this is the length of the conductor, and this is the area of cross section of the conductor. Okay. So if we consider that V is equal to IR, then you get V is nothing but, we substitute this rho L by A into this. So you get V is equal to I into rho L divided by A. Understood, right? So V is equal to I into, but V is nothing but, this is the potential between this to this. You have an electric field E, and the length of the conductor we consider this is a L. Okay. If the length of the conductor is L, then V is also given by electric field intensity multiplied by L. So you got V is equal to this and V is equal to this also. By equating these two, we get EL is equal to, that is this EL equal to I into rho L divided by A. So this L gets cancelled. So you got E is equal to I rho by A. Okay. So this particular thing is called, we call this entire thing as J rho. E is equal to J rho. Rho is resistivity, J is called current density, because this is called current density. That means amount of current divided by the area of cross section, area of interest. Okay. So if you take that, that is called a current density. This is a popular 1 mark question. So how is the relation between the current density and the electric field? Okay. So E is equal to J rho. If we do the other way around, that means I write E is equal to J rho, and I write J is equal to E divided by rho. That's equal to 1 by rho into E. Okay. And this 1 by rho, J is equal to 1 by rho is replaced and put as sigma E. So sigma is called opposite of the resistivity. This is called the conductivity. So all these are 1 mark questions. That's why I'm just specifying them. Simple definitions. Okay. So that is, I am in a page. That's Ohm's law. Can I repeat that? Oh, this one. This is Ohm's law. This one. I and A. That's what is a J. Okay, I understand your question. So this J is nothing but I divided by A. That's what I wrote here. Amount of current divided by the area of interest. I by A is the current density. Okay. So we have now, from the same relation, we got this. J is equal to sigma E, and sigma is called the conductivity. Okay. Conductivity of whatever of that particular conductor. Okay. So rho is characteristic of the material. This does not depend on length, area or whatever, it does not depend. Okay, so if you say, for example, whatever is the length, but for every copper material, it can be 1 kilometer copper or 1 centimeter copper, both of them will have the same amount of rho. Rho is same for both, it doesn't depend on length. Okay, same goes with the conductivity also. Conductivity is a material property. So the next section, 3.5. 3.5 is a little important, okay, meaning sometimes they give this derivation as well. Okay, so we will have to go slowly, step by step for this particular thing. That's why let's go to that page where it is written. Okay, so he has got a random movement of the electrons which is given like zigzag in that picture. Okay, and what happens in a conductor is electrons will be moving, electrons which are free electrons, so they will be moving like different directions. If you have electric field is this, so electron will be moving, and let's suppose there is ion, it will go and hit that ion, and that is called collision, and it will go in a different direction. The speed remains same. Okay, so that means they keep on colliding between various collisions, okay, or between various ions. Okay, so we are talking about the topic, what we are talking is drift velocity. Drift velocity, this velocity is about the electron. Okay, so the free electrons in a metal, they keep on moving in that zigzag manner, and then they will have a collisions with the static ions, stationary ions. The ions are stationary. So the speed remains same, speed is same, but then the direction changes. Direction changes. Whose direction? The electron's direction changes. Okay, let us suppose this is, we are talking about if the electron is actually in one direction, then you will have, for example, electric field is in this direction. So if you remember, the force due to electric field E on a charge Q. So we remember, we did this, F is equal to EQ, capital EQ. So I asked you to remember F is equal to EQ. Okay, in this case it is electron, so the charge of electron equal to minus E. Therefore the force due to this electric field is nothing but minus E, capital E. Understood, right? This is the force created by the electric field already there, but then electron also is moving with some velocity, right? So if electron is moving with some velocity, the force with which the electron gets pulled is given by, because it's moving, F is equal to ma, Newton's second law. Got it, right? Therefore you equate this fellow and this fellow. ma equal to ma, this force must be equal to the other force, minus E, electric field. Therefore acceleration A is given by minus E, capital E, divided by m. Any question on that? This is equation 3.15. If you refer the textbook, this is that equation 3.15. Okay, so what he's trying to say here is that if there was initial velocity immediately after the last collision, then its velocity vi at a particular time is, this is the difference in velocity. Okay, so after each collision there could be some, in case of electric field, therefore actual velocity v is given by initial velocity minus whatever is the current velocity what we are talking about, Vi, this is, I think, let me use that formula. Final velocity is V. Initial velocity is U. So A is acceleration, T is the time taken. So we know that V is equal to U plus AT. This we learnt, right? So in this case we are getting acceleration as a negative one, right? We substitute this acceleration, this value, into this. Okay. So what we will get here, A is negative, and therefore final velocity is initial velocity minus E divided by m into t, time taken, whatever is the time taken. That's what we have. That's equation 36. Okay. Therefore the drift velocity, meaning between each collisions there will be slowing down or the velocity may be increasing. Therefore what they call that average velocity of the electron between the collisions is called a drift velocity, and we call that as a Vd. We give that symbol as a Vd. So if I have Vd, drift velocity, that means the initial average velocity minus whatever you are getting, this acceleration, multiplied by the time. This is also average time taken between the collisions. This is average time. Okay. So this is what we get. Average velocity Vd is the expression you got, page equation 317, page 98. Okay. So with this what we get, if the time, that average value of t we consider as a relaxation time, if this Ti average is represented as a tau, which is called a relaxation time, then we have Vd equal to minus E, this is 0, okay, minus E, capital E, divided by m into tau. I just replace the Ti average with the tau. Okay. So in general the meaning of drift, meaning, so let's suppose we are very thin. We are walking on the road. We are so thin that if there is a heavy wind, we will be moved away by the wind, but we still have some weight, moved away by the wind. So sometimes we may move towards left, sometimes we may move towards right. So like that you get drifted off on the road. That's how the word drift comes into the picture. Okay. So if you look at the paragraph he talks about now, with the picture 3.4, there is an electric field given going right to left. Okay. And let us suppose with this drift velocity you got a conductor there. This is a conductor. With this drift velocity the electric field is here, and this is the distance covered. For example, this is the distance of the conductor covered. We know that distance traveled is nothing but velocity multiplied by time. Therefore this can be given as drift velocity Vt multiplied by time, if the time taken is t to travel that much thing. Any question on that? No, right? No. Okay. So now we know that we are considering as a delta time instead of total time. In delta t seconds delta x is equal to, so see, after this expression we have gone to this picture. In that picture we have talked about this. In delta t seconds we write delta x is equal to Vd into delta t. Okay, so definitely during the delta time there will be some current. Let's say I is a current in that, then I delta t will be nothing but the charge delta q. Okay, delta q. So how do we get this delta q is whatever is the area of cross section, delta q is nothing but the total charge in that volume. So volume, right, this entire volume. Okay, how much ever is the charge, that is nothing but the delta q. So what we have is, my steps are slightly different, that's why better to follow this. I is equal to delta t, that's equal to delta q, and this is what is the total charge I said. How do we get the total charge? Let's suppose there are n number of electrons. Okay, that means n number of electrons. Okay, multiplied by, they are moving into the area of cross section A multiplied by delta x. So for example, it's a cylinder and this area of cross section is delta A, sorry, this is A. Okay, and then if this is the delta x part, then how do we get actually area? If it is a circle, we'll just say pi r squared, and this is h. Okay, we have pi r squared h is the volume, isn't it? So that's why we write A delta x. So now I substitute back n e A delta x. Just now we said delta x is nothing but Vd into delta t. I delta t is equal to this. So this is the expression what you see, the equation 3.18. That's the equation, you have it. Okay, so we already put that what is the value of delta E. If you go back, right, Vd, the drift velocity, we had the formula. So we have drift velocity, go back to this, this is the drift velocity. Okay, this is the drift velocity, minus E divided by t, tau, whatever. So then I substitute that here, I delta t, I am substituting for this Vd, n e, so n e a into minus e divided by m tau delta t. So this is what I substituted. Okay, so you have one e here, another e here, and if I take off this negative sign and I put as a mod, by absorbing the negative sign, mod e will take care of the negative sign. Okay, so you get I delta t equal to n e squared e squared is coming from here and here. Okay, e squared a, okay, divided by m. I'm just rearranging the things, e squared a divided by m. So this is taken, this is taken, a is taken, m is taken, write down as a mod e for e. Okay, then whatever is remaining is tau, this is tau n delta t. So that's the expression what you see, that's an equation what you see at 3.19. Okay, so 3.19, that gives I delta t equal to the entire thing. Okay, so we learnt that there is a current density. We had I is equal to J, this is the current density, divided I by A. We just had the previous, therefore I is replaced with mod J into A delta T equal to E squared A by M tau n delta T into electric field mod. So this A and this A get cancelled. So what you have remaining is n E squared by M tau and E. Okay, that is what is nothing but, so delta T gets cancelled. Okay, now the current density is given by n E squared by M. The density J is equal to, so n is there, n E squared, this n E squared by M. Okay, so tau is there and delta E is there, so mod E is there. So we have gone back to the same thing. Earlier we tried to give a relation. If you go back to this very beginning, right? So we got J is equal to sigma times E, and we have got some conductivity like that. Now the conductivity itself, using the drift velocity, we got a derivation that this entire thing must be the conductivity, since J is equal to sigma E. Okay, sigma is equal to n E squared by M tau. Okay, so this is how we are actually giving the conductivity using the drift velocity. So this kind of a derivation, not in the boards. I think one time they asked in the board, other times in the college examinations they definitely ask for this. Any questions or any doubts? No? Now we go to page number 100. Page number 100, he is talking about mobility. So this is a mobility. Obviously the mobility is a characteristic of whichever is the charge carrier. Mobility is defined as the magnitude of the drift velocity per unit electric field. So it is defined as magnitude of velocity per unit electric field. Per unit electric field. So we know the expression for VD and we know what is E. Okay, so if I divide this with the other, that means mu, that mu is the symbol for mobility, magnitude of VD divided by the electric field E. So SI unit of this is meters volt second, meters divided by volt second. This is the SI unit of it. Okay, so VD, we know the VD value, you substitute that into that. VD is equal to E tau E by M. Okay, so substituting VD or magnitude of VD equal to, so small e by M into tau. So we substitute that here, so that mu is equal to, so E by M into tau divided by this E. So E gets cancelled. So you have mu is equal to, this is electron charge E tau divided by M. Okay, so tau is the average collision time for the electrons. So you can define tau collision time for electrons. So that is about the mobility. Now see the three graphs what are given on page 101, 3.5, 3.6, 3.7. You just need to look at the pictures. Okay, if a particular thing is a ohmic device, that means the devices which obey the Ohm's law. So V is directly proportional to. So now we are talking about the limitations of Ohm's law. So if you draw the VI graph for a particular perfect resistor, then you will see the resistance. So this is for a resistor, pure resistor, okay, and this is I. But in reality it will be like, to some extent it will be a straight line, but in practice after that it breaks down like that. So that's why you will see in the graph, right, the relation between Vi and I depends on the sign of. In other words, if I is a current for certain V, then whatever. So in a diode, for example, if you look at 3.6, this is for a resistor. Because resistor is a ohmic device. It's ohmic. That's why you have a linear relation. If it is a diode, then you will see the graph which is in 3.6. What it means is, you have this is for diode. Diode is an electronic device. Okay, so the current is actually in terms of very small, is the I, is a voltage. So initially the current will be, for a small voltages it will be like that, okay, and suddenly this will go like that. As the voltage increased, I will tremendously increase. So this is a curve, not a line. That means this is a non-ohmic. This is a non-ohmic device. When they say diode is example for non-ohmic device, this is how the characteristic would be. And if you give a negative current, it will be like that. That's for the negative current. Okay, so the current is in the order of, this is microamperes on this side, this is microamperes on this side, it is a milliamperes. So that means if it is milliamperes, you don't even see this actually. Okay, that's for diode. Then if you look at the 3.7, it is actually varying. Okay, it has got, for some part it is a straight line, for some part it is a curve. Okay, so for a gallium arsenide, GaAs means gallium arsenide. The gallium arsenide, the relation between V and I is not unique. You see the point C there. There is more than one value of V for the same current. This means the material exhibiting such behavior is a gallium arsenide. Materials and devices not obeying Ohm's law in the form of equation 3.3 are actually used in electronic circuits. Done. The next part is a table. Resistivity for different materials. You don't have to memorize this materials values, which is the table 3.1. Don't have to memorize that, but look at how the resistivity is varying. For a silver, it's 1.6 in 10 to the power of -8. Whereas you go for hard rubber, the resistivity is very high. Resistivity is very small for silver. That means it conducts better, whereas pure water resistivity is very high. For a glass it is very high. Okay, so that means if the resistivity is very high, you will have a resistance which is multiplied by length and area of cross section divided by area of cross section. You will get R, rho L by A R. If R is very high, then current going through will be very less. So silver will not allow the current to pass through much. Okay, silver not a good conductor. Resistivity is high, R is high. Therefore, I will be less based on V is equal to IR. Okay, so that is the table what we need to know. The resistivity as such varies with the temperature, that we will talk in the next section. Before that, there is small resistors. Actually they are called carbon resistors. Okay, if you are the person who does some electronic hobbies and all, small circuits we build and all, so if it is a electrical wiring, that means we have domestic wiring. It comes and then you put a bulb here and like this, right? This is a wire, this is a copper wire. Okay, or it can be anything, it can be aluminum wires. Whereas in electronics circuits, actually there is a thing called a track, that's a copper track or some other metallic. This is in the printed circuit boards. Okay, after that if you want to have a resistors, then they will have a very small thing, okay, such a small thing that is connected. Some markings on this, these are called color codes. So by looking at the color code of a carbon resistor, we will be able to tell what is the value of that resistor value. So there is a mnemonic to remember this. You see that page 103, and he has given the colors. Okay, so this color code, carbon resistor small in size, and hence their values are given using a color code. See, if you look at the first letter of all these colors, right, black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, afterwards no color. So you see on the right side he has given, these are like a bands on a resistor. There are two pictures given, 3.8A and 3.8B. Okay, how do we remember this? If you see that first letters I said, right, so I'll write it, you can see that whether that is correct or not. Okay, you got B, Roy, you see BB Roy, and you have a GB, okay, Great Britain, and sorry, Violet, okay, then you have G, and you have got W and G again, and yes. Of course no color, you don't need to remember. So no color, actually after G, gold, silver and all, you don't have a value. So you only have up to W, right? So BB Roy, okay, went to Great Britain, B.B. Roy went to Great Britain to have a very good wife. That's how they remember. Okay, B.B. Roy went to Great Britain. B.B. Roy went to Great Britain. I can write it for you. Okay. Great Britain to have very good or glamorous, whichever you want to write it. Very glamorous wife. So this, okay, this, okay, and this. Okay, now the values will be, so the first one starting with 0. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now look at the how he describes that. The first two bands from the end indicate the first two significant figures of the resistance in ohms. Okay, so if you look at that, gold and silver, in the table he said 10 to the power of minus 1, 10 to the power of minus 2. That means you will be multiplying this with that. Okay, so now read the picture 3.8. You see red, silver. So that picture says 3 reds, red, silver. Correct. So the color coded resistors. So he says red stands for 2. This is 2, 2, 2. Silver, it is to be multiplied with 10 to the power of minus 1. Right, silver with 10 to the power of minus 1. That means this is 22.2. 222 we got, correct. So that is 2200. Okay, because we have a silver here and silver tolerance is 10, that is a 10% tolerance, and we are to multiply with, multiplier is gold is 10 to the power of minus 1, this is 10 to the power of minus 2. Okay, so this minus 2. So you multiply this with, so that's what he is talking about. You will have 22. So the last band stands for the tolerance or possible variation percentage above the initial values. The first two indicates, right, 2200. We have the 00. That's what is that 00 is to be added. Okay, so 22. This is a tolerance. Okay, and I think the silver stands for the tolerance, which is 10% tolerance. Okay, so this third one is 10 to the power, okay, 10 to the power 2. Okay, so 22 into 10 squared. Okay, and this is the ohms, and this one is 10% tolerance. Now you take the next one, yellow, violet, brown. So the next one was violet, brown, and then the gold. Gold is a tolerance. You look at yellow, it's a 4, violet is a 7. Okay, so 4, this is 4, 7, B. Okay, so he said it is a brown. Brown stands for 1. So this is 1. Okay, so that is 10 to the power of 1, right? So this third one goes for 10 to the power of 1. So you'll have 4, 7 into 10 to the power of 1, and the gold, that means 20%, 5% is the. 5% tolerance. So this is how it is to be read. It is very important if you are actually buying resistors from electronic shops and all the things, because you have to use the right resistance in the electronic circuitry to have a correct functioning, and that's the reason this is relevant and important for the students to know. Okay. The next one, temperature dependence of resistivity, 3.8. Okay. So if you look at the page 104, the resistivity definitely varies with temperature. He has given one for copper, the second one for nichrome, the third one for a semiconductor. All the three graphs are important, and the equation 3.26 is important. What is that equation? So the resistivity depends on temperature. So that's why he gives rho at a particular value. So rho at a particular value, that means rho at a temperature T equal to rho at 0, he says. Okay, that means at temperature T0, that's what it means. So rho 0 and multiplied by 1 plus whatever you have here is called the coefficient, the temperature coefficient of resistivity, alpha. That's alpha within the bracket, the difference between T and T0. Okay, now let's look at this. The equation is to be remembered. This equation is to be remembered. So T is in Kelvin. Temperature T is in a Kelvin. Okay. So rho 0 is resistivity at T0, alpha at T0 temperature. Alpha is called the temperature coefficient of, okay, so the temperature coefficient of resistivity, temperature coefficient of resistivity. And T is greater than T0, then you have rho T at that temperature equal to this and this and this. So if they give you something, that T0 and all the things, you substitute and we get this particular thing. So now if you look at the graphs, that figure 3.9, 3.10 and 3.11. So the graphs are to be remembered, the shape of the graphs. Okay. One is the resistivity is very, very low up to the room temperature. I am reading the graph 3.9, and after the room temperature it starts increasing. So it starts increasing and follows as that particular thing for copper. So the first graph is for copper. I am not drawing the graphs. Okay. The second one 3.10. See, the resistivity is 0. That means at a very, very low temperatures or hundreds of K. That is for nichrome and goes as a straight line increase. Whereas the temperature, the rho will decrease for a semiconductor. Okay. So for a semiconductor it decreases as shown in the graph. Done. Okay. Then the next part is a little revision of what we have done in the 10th standard. In ICSE we have done this. Okay. So that is nothing but energy, electrical energy, okay, electrical power. So obviously energy, work done, and the power. So you look at the page 106. The change in the potential energy in delta T to move from A to B, that means, or B to A for example, A is at a different point, the potential difference between 2 points A and B is VA minus VB, which is greater than 0. Okay, current is flowing from A to B, that means A is a higher potential, B is at a lower potential. Therefore, potential energy, which is actually opposite, right? The potential energy is given by delta Q multiplied by the potential difference. He writes as a minus V because VA is greater than VB. So that's the reason he writes delta U, that is a change in the potential energy, equal to minus delta Q into V. And he writes Q is equal to delta Q is equal to I delta T. And therefore you get minus I V delta T. So if the charges are moving without collisions through the conductor, their kinetic energy would also change so that the total energy is conserved. Okay. So K is the kinetic energy, the delta K is the kinetic energy, that is in the opposite way, that means it's a negative of delta U potential energy. So when you add it up, you get 0. And therefore delta K is equal to IV delta T. So that is about the kinetic energy. So change in the power or delta work done or the delta energy dissipated is nothing but IV into delta T only. Whatever is the energy you are getting through kinetic energy, and that is the equation he writes 3.31. Delta W is IV delta T. It's the same thing, he just put delta W, that's it. So if you want to find out P, what is P? Electrical power. That is how much is the energy dissipated in a unit time. So your delta W divided by delta T. So you will get IV. So P equal to IV. Using Ohm's law, V is equal to IR, we get P is equal to I squared R, that's equal to V squared by R. So you may be wondering, what's happening, sir is not explaining these things. All this thing is covered earlier. Okay. Other than the delta we are writing here, everything else is known to you. It is very, very easy to remember. Section 10. Combination of resistors. Anyway, I'll be giving you the short notes, all that questions, 2 marks questions, 3 marks questions, those things anyway to you later. Okay, notes. Combination of resistors, series and parallel. Okay, this also we studied. Series resistors, equivalent resistance R is equal to R1 plus R2 plus R3. In case of parallel, 1 by R parallel equal to 1 by R1 plus 1 by R2 plus 1 by R3. Right? Remember doing this in the 10th standard? The derivation is exactly the same thing. There is no change. But if you want the derivation, I will be sending it to you. I will write that now for you. So, shall I write it or you will be able to understand it? So resistances. So what we talked earlier is in series or in parallel. This R series equal to R1 plus R2 plus R3 and so on. Here parallel equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Okay. So is there any message for me? So that's 1 by R1 plus 1 by R2 plus 1 by R3. Okay. So I am not looking through the derivation. It's easy. Generally they don't give this. Okay. You are just applying the Ohm's law and then you write it actually. Okay. So the energy also we have done. Next comes cells EMF internal resistance.